It's a great privilege for me to have the opportunity to participate in this tribute to Bob Woodward, whose work, I believe, was an inspiration to every organic chemist and truly to every scientist. Today I'm going to tell you some of the very recent adventures that students in our research group have been having, primarily in the area of organic synthesis of molecules of a very peculiar and interesting kind. And in order to concentrate on this more recent material, I'm going to have to ask you to accept a certain number of statements that I make with less than the customary scholarly documentation. In other words, I'm going to make some statements that you may want to argue with. We think that these statements are correct, but I won't have time to justify every one of them. And I'll try to point those out as we go along. There will be a certain amount of hard fact in today's lecture, however, and about these I make no excuses. Now, this slide shows a group of molecules that we have been working on for a number of years now, and about which we think we have reached some understanding, some level of understanding. There are 4 of them. There are 2 biradicals here. One of them is a triplet substance with paired spins of the electrons. Another is a singlet molecule. And we believe that both of these species are true local minima. That is to say, these are not transition states, but they do have finite lifetimes. And I'll have more to say about that in a moment. The 2 molecules to which these biradicals are connected are the ones shown at the upper right of the slide. This is a bicyclo-310-hex-1-ene with a bridgehead double bond here. And at the lower left, an alkylidene bicyclo-210-pentane. Now, these 2 hydrocarbon systems are extremely strained. We don't know the exact strain energy, but we guess that in the molecule at the upper right, the bicyclohexene, the strain energy may be 75 kilocalories per mole. There's another very peculiar thing about this group of molecules, and that is, of the 4 of them, the most stable species is the triplet biradical. And in these hydrocarbons, the bicyclic hydrocarbons, we have reached, we believe, the border of covalency, because these compounds are less stable with this bond intact, or that bond intact, than they are with it broken. And that means that the global minimum here is a non-Kekulé substance. So this is a, if you will, a violation of Kekulé's rules of valence. Now, the facts and line of argument that lead us to make these statements, which you may think to be outrageous, are given, at least in preliminary form, in the literature, and I won't have time to go into them today, but I do want to show you the energetic relationships that we believe to prevail among these molecules. The numbers here have been derived by successive approximations over a period of years. They are subject to change, as is any datum, but they are the best that we have available now. In some cases, we don't have exact numbers, but merely inequalities. The zero of energy I'm just arbitrarily putting here at this alkylidene bicyclopentane. The bicyclo-310-hex-1-ene system is less stable than that by an amount that we don't know, so we just put it higher. It's higher than 0. The singlet biradical is approximately 13 kilocalories per mole higher in energy than the bicyclopentane. And the triplet biradical is lower than this one by some amount whose exact value we don't know, but we suspect may be at least 1 kilocalorie. So these 3 substances are very close to each other in energy, probably, This one is considerably higher in energy. Incidentally, this energy separation between the singlet and triplet biradicals is considerably higher than we at first thought it was. And it is now reasonably close to the values that are being calculated by the most sophisticated quantum chemical means. But the value of this energy is an experimental number. I want to emphasize we don't do calculations of that degree of sophistication, but there is some gratification in the correspondence of these two approaches. Now, separating the bicyclo-210 pentane from the singlet biradical is a transition state whose energy is approximately 2 kilocalories higher than that of the singlet biradical itself. At a higher level, how much higher we don't know, but higher than this transition state is a transition state leading from the singlet biradical to the other bicyclic compound. This 2.3 kilocalories per mole energy gap is something that we can measure. It is, in fact, one way we can measure it roughly is by the difference in two activation energies measured kinetically. One of them, the energy for opening this bond in a reaction leading to the singlet biradical, and another, the activation energy for going from this compound to the singlet biradical to the triplet molecule. The difference in those two activation energies can be shown to be, to a pretty good approximation, the value of this barrier. The barrier can be detected, although not directly measured in magnitude, by trapping reactions that we will show you in a moment. But I want to emphasize that although this barrier is extremely small, it is nevertheless finite. And it may be, in fact, although one has to be very careful about priority claims, we think there are certainly very few examples in which a finite barrier to the closure of a singlet hydrocarbon biradical has been demonstrated. We don't take the position that this barrier is typical of such barriers. In fact, we think it is rather large for such a species. And in particular, the barrier in the simple trimethylene biradical itself, we believe, must therefore be lower than 2.3, probably quite a bit lower, very close to zero. Now, that barrier has a practical consequence in that it is the thing that has allowed us to carry out the chemical transformations that identify the presence of this species. Were that barrier much lower, it would be very difficult, if not impossible, to intercept this thing. The value of this barrier predicts a lifetime for this molecule. The disappearance, unimolecular disappearance of this molecule in the absence of a trapping agent consists of cyclization to this one and intersystem crossing to the triplet. The sum of those two rate constants, the reciprocal of that, is the average lifetime of this species. And from the numbers that we have available for those transformations, we can predict roughly a lifetime of 100 picoseconds or thereabouts for this species. Now that is, with modern fast kinetic techniques, a spectroscopically detectable species in principle. And I wish that I could report to you the outcome of an experiment that is currently underway in the laboratory of Dr. Peter Rentsepis at Bell Laboratories, which constitutes an attempt to detect this species and measure its absorption spectrum, which incidentally has been predicted in advance in the literature by Goddard and Davis. Unfortunately, that experiment is not quite finished, although I cannot forbear to say that the results are extremely encouraging at this stage. Now, the chemistry of these species can be entered in the triplet case by following a device that was first worked out in the case of the trimethylene methane biradical itself by Paul Dowd in the late 1960s. We've merely adapted his procedure to this bicyclic diazine, and when that material is irradiated in a glassy matrix, one can generate a strong signal that we have ascribed to the presence of this triplet molecule. The EPR spectrum intensity follows the Curie law, which is shown here, and all that tells you is that there is no singlet state that is populatable thermally through the temperature range that is available for investigation. When this species is either photolized or heated in fluid medium, it gives rise to a series of dimers derived from this triplet molecule. And those same dimers can be obtained when this low temperature photolytic preparation is allowed to melt. There's no question that this photolysis produces massive amounts of triplets. In fact, this reaction is essentially quantitative at the low temperature. Now, some of you will recall an experiment in the 1950s by Kriege using a diazine similar to this, but without the exocyclic alkylidine group. And in that photolysis, the nitrogen was eliminated and a new bond was formed here. That is to say, bicyclo-2,1,0-pentane itself was the product of that reaction. And one might ask whether that same trick might not be used for the synthesis of 5-alkylidine bicyclo-2,1,0-pentanes. When we made these observations on the triplet, it was an unfortunate consequence that this very exciting EPR observation muddled our thinking about the possibility of closing this bond, because the low temperature photolysis ought to be the best way, one would think, of making a very unstable molecule. And we expected that bicyclic hydrocarbon, or the other one from ring closure here, to be very unstable molecules. And so the logic of this idea was that if one was making the triplet quantitatively at 77 K, there was no hope of closing this ring at a higher temperature. But as is usually the case, the excuses that one makes up for not trying an experiment don't hold water. That was a favorite expression of Professor Woodward, many times repeated to those of us working in his laboratory. And so it proved in this case, because the photolysis of this diazine in fluid medium at a much higher temperature than 77 K, in fact, does give rise quantitatively to this 5-isopropyladine bicyclo-2,1,0-pentane. At minus 78 degrees, this is a stable molecule, despite the fact that at minus 196 degrees, the triplet is formed. Now, the reason for that is this very simple fact that I told you earlier, namely the thermal barrier to the closure of this biradical. The thermal barrier for intersystem crossing is probably close to 0. The barrier for ring closure is finite, about 2 kilocalories per mole, so the product composition is going to be temperature dependent, and in fact it is, and it changes from almost completely this at minus 78 to almost completely this at minus 196. That's a tricky thing that we did not discover until much later than we should be proud to confess. But it does provide us with a way then of generating these compounds. Now, as I mentioned, this compound is thermally unstable at higher temperatures. Above about minus 40 degrees, it breaks this bond, goes back to this biradical, undergoes intersystem crossing to the triplet, and the triplet then dimerizes. And one can study the kinetics of that process and of the dimerization of the related methoxy compound, shown here at the top of this slide. The products of these reactions quantitatively are the dimers of the trimethylene methanes. The activation energies here are 13.2 for the dimethyl compound and 16.9 for this methoxy compound. We don't know the cause of that small difference, but we believe it's real. The interesting thing are the pre-exponential terms, which are approximately 4 or 5 orders of magnitude smaller than they should be for a thermal unimolecular reaction. These reactions are clean first-order processes. The rate-determining step then involves the formation of some reactive intermediate in the unimolecular step. And if that were a spin-allowed reaction, we would expect a pre-exponential term here of about 10 to the 14th. We interpret these low pre-exponential terms as being associated with the necessity to form the triplet biradical, which is the actual precursor of the trimethylene methane, of the dimer of the trimethylene methane. Now, this behavior is strikingly different to the kind of thing that one sees with one additional methylene group in this larger ring. This is work of Gajewski and of Roth. There are many other examples in the literature of methylene cyclopropane rearrangements and stereomutations. I just picked these out to indicate that you can roast these molecules at high temperatures for a long time. You never get any trimethylene methane dimers from them. So the intersystem crossing in this system is very slow compared to all the other processes that can go on. And the pre-exponential terms here are about what one would expect for a thermal unimolecular spin conservative reaction. Now, the chemistry of these alkylidine bicyclopentanes can be outlined here. First, let me point out that one can make cycloadducts of the structure shown at the bottom of the slide here by carrying out the thermal decomposition of these diazines in the presence of an olefinic trapping agent. Here is the case with acrylonitrile. Above 50 degrees, nitrogen is eliminated and the intermediate biradical is trapped, or this reaction can be carried out by photolysis of the azo compound in fluid medium at -78 in the presence of the trapping agent. In both instances, one obtains these cycloadducts to position isomers of the cyano group. The intermediate in the formation of these cycloadducts is not the bicyclopentane. That's fairly simple to demonstrate because it does not react with acrylonitrile at -78 degrees. However, it does react with acrylonitrile at -55 degrees, and it gives exactly the same products. So at higher temperature, this species is capable of going to something else that can give that. Now, what is that other thing? We'll come back to that question in a moment, but let me point out first that this is not the first instance by any means of the cycloaddition reaction of a strained sigma bond with a pi bond. I believe the first work along that line was actually carried out by Paul Gassman and his co-workers in the 1960s. This is maybe a little too big to get on the slide, but there is a date down here, 1968, right, thank you. Now, at the top of the slide, I show the reaction that Gassman and Mansfield studied. That is a reaction between propiolic ester, the head of which is been removed by the edge of the screen, and bicyclo-2,1,0-pentane itself. The kinds of products that they observed are shown here. Two of them are formal ene products, and another one is a cycloadduct. Now, note that the kinetics of this cycloaddition reaction are, as reported by Gassman and Mansfield, second order. First order each in the hydrocarbon and the olefin. And there is no sharply responsive solvent effect. That is to say, in polar solvents, the rate is about the same as it is in nonpolar solvents. The mechanism that they proposed, and a similar mechanism was proposed by Cairncross and Blanchard, who studied the cycloaddition reactions of the next lower homologue, namely bicyclo-1,1,0-butane, involved a bimolecular interaction between the strained hydrocarbon and the olefin, giving a biradical intermediate, which then could lose stereochemistry, which it did when the olefin was stereochemically labeled, and it could then cyclize or transfer hydrogen to give the products observed. Now, the crucial point here is that this mechanism is a bimolecular, then unimolecular process, not the alternative that one might have anticipated, namely a unimolecular process breaking this bond and giving a biradical, which then was captured by the olefin. That process was specifically ruled out or rejected by these workers. Now, I certainly have no reason to quarrel with the conclusions drawn here. They certainly are consistent with the information given. But this is not the only mechanism by which strained hydrocarbons react with alkenes, as we'll see. Now, on this slide, I outline two kinetic possibilities for the reaction of the alkylidene bicyclopentane with acrylonitrile. One of them is the same mechanism, would have the same overall kinetics as the mechanism proposed by Gassman and by Cairncross, and that is a bimolecular process, mechanism A, in which a collision between these two is required in the rate determining step. What may happen after that, whether biradical intermediates are involved, one doesn't know, but the brutal overall kinetics would be second order. Now, an alternative mechanism is the one involving a bond cleavage as the first step to form the biradical intermediate. This species, we believe, must be a singlet for a substantial number of reasons, which I don't have time to go into. The chemistry of this entity, as reflected in the cycloaddition reactions we're talking about, is very different from that of the triplet biradical. This singlet biradical can either return or be captured by an olefin. Now, that is a reaction which does not have clean second-order kinetics, at least not under all conditions. And in fact, this mechanism B mechanism B can have a kinetic pattern that depends upon the individual circumstances, as shown here. Mechanism A, as I mentioned a moment ago, would predict the second-order kinetic pattern. If one carried out that cycloaddition under pseudo-first-order conditions in the presence of a large excess of the trapping agent, then the observed pseudo-first-order rate constant would be directly proportional to the concentration of the trapping agent M with some second-order rate constant K3. And in a double reciprocal plot, that would have this form. It would be linear, but the intercept would be 0. Now, in contrast, the two-step mechanism involving the preliminary formation of this intermediate, mechanism B, would have kinetics shown here. In the double reciprocal plot, again, this would be linear with the reciprocal of the trapping agent concentration, but there would be a finite intercept. And that finite intercept is, in fact, the reciprocal of the rate constant for the ring opening step. Now, depending upon which step is rate determining, this reaction can either take on second order or first order form, and if neither step is rate determining, that is to say, if there is no well-defined rate determining step, the kinetics can be intermediate. One should expect to see first order behavior when the rate determining step is the ring opening, and that would be the case when the trapping agent is sufficiently reactive to capture the biradical every time it's formed. On the next slide, I show the results of a double reciprocal plot of this pseudo first order rate constant against the trapping agent reciprocal trapping agent concentration for two different trapping agents. The upper one is acrylonitrile, and the lower one is maleic anhydride, which is a far more reactive trapping agent. These data fit very well for the exclusive operation of mechanism B, the two-step mechanism. Because the intercept is finite, it is essentially the same intercept for the two trapping agents, and the more reactive trapping agent leads to essentially first-order behavior, that is to say, a zero slope. So the chemistry of alkylidine bicyclo-210 pentanes, at least as I've outlined it to you so far, seems to be well described by a mechanism shown here, in which there is a reversible unimolecular ring opening to give this biradical intermediate, ring closure of which is opposed by a small but finite barrier, which permits the interception of this species by a trapping agent. That trapping agent has to react at nearly the diffusion control limit in order to be compatible with other information that we have. And if it is not trapped, it undergoes intersystem crossing by an electron flip to give the more stable triplet biradical, which also can be trapped by the trapping agent to give cycloadducts. But if no trapping agent is present, this just dimerizes at these two positions. So that's alkylidine bicyclo-210 pentanes, at least as far as we knew them until very recently. Now I'm going to return to some special molecules in this class in just a few moments. I want to discuss with you now some attempts that have been made recently in our group to come to grips with the problem of this much more elusive, even more elusive molecule, bicyclo-310-hex-1-ene. I don't know if I have control over the focus here. No, I have no control over the focus. But perhaps can you focus that? Thank you, that's good. This molecule was first generated by Kerbrich and Heinemann as a reactive intermediate by an ingenious cyclization, which I show here in modified form. They generated an alkylidine, vinylidine really, in a molecule which contained in a remote position a double bond onto which cyclization could occur. And that alkylidine was generated by alpha elimination. They actually used the vinyl chloride. We have modified this slightly to use the dibromide. Now, these dibromides, I point out, are prepared by a kind of Wittig procedure from the corresponding ketone. This is following a recipe of Posner, and this works quite well in many instances and gives us access to structures of this type. And when these are treated at low temperature with butyllithium, one can generate these species. Now, Kerbrich and subsequently our own work confirmed that, showed that when you generate that particular compound with two methyl groups here and another methyl group on this double bond at low temperatures, at minus 78 degrees, for example, the bicyclo-310-hex-1-ene system holds together because the dimer that you obtain, the principal dimer that you obtain, has this pi plus pi structure. That's an orbital symmetry forbidden reaction taking place at minus 78 degrees. And you see why I'm really unqualified to talk about the topic that Martin Saunders originally announced. But it just goes to show how fantastically reactive this double bond is. We have also found another isomer. Incidentally, there's a methyl group missing here at that point, which is a product of the dimerization of this, in which the sigma bond of one molecule adds to the pi bond of the other, so that we have one open system and one closed system. But these are the products at low temperature. Now, Kerbrich noted, and we also have found, that if this reaction is carried out at higher temperature, namely 0 degrees, one gets dimers of the trimethylene methane that is formed by cleavage of this bond. Now, it is this set of observations that has started us on a search for these compounds. That is, what one would like to do is to actually have these in a bottle and find out what their properties are. If you generate this substance at a temperature intermediate between 0 degrees and minus 78 degrees, namely at a temperature at which the bicyclo-210 pentane, alkylidine bicyclo-210 pentane, shown here, is reasonably stable, or stable for a few minutes, it is possible to observe the NMR spectrum of that species. And the way this experiment is carried out is to carry out the Kubrick cyclization at minus 30 degrees. That generates this species. This bond breaks. A new bond forms here. In other words, this is a methylene cyclopropane rearrangement. And this rearranged compound is sufficiently stable for a few minutes at minus 30 degrees, so it can then be cooled back down to minus 80 degrees, where it's indefinitely stable. And one can see the NMR spectrum of this, among other things, in the probe. Now, the other things that you get are the dimers that are formed from the corresponding trimethylene methane. If one adds to that reaction mixture, having kept it cold, one adds a trapping agent and then allows it to warm to room temperature, one can isolate the cycloadducts of the trimethylene methane. So one of the kinds of chemistry, unimolecular chemistry, that bicyclo-310 hexenes are capable of doing is undergoing this methylene cyclopropane rearrangement to the more stable alkylidine bicyclopentanes. And this is one of the pieces of evidence that leads us to the statement that the energy of this is lower than the energy of that, because this rearrangement is apparently unidirectional. Well, now, one of the things that people do in attempting to cut down the reactivity of extremely reactive molecules is to put tertiary butyl groups on. And we have had some experiences along this line. This tertiary butyl ketone would be a desirable precursor of this tertiary butyl substituted bicyclo-310 hex-1-ene. This should be a compound with a diminished reactivity of the double bond because that bulky substituent is there. Perhaps we could isolate it. Well, difficulty immediately presents itself because the synthesis of these dibromoalkene precursors needed to apply the Kubrick-style ring closure doesn't work with a tertiary butyl group next to the carbonyl. This Wittig reaction fails completely, and this line of approach seemed to be shut off to us until quite recently. And what has made this all possible is the extremely interesting observation by Professor Jack Gilbert and his co-workers at the University of Texas that one can generate the equivalent of a vinylidene by a kind of Wittig reaction between a ketone and dimethyl diazophosphonate. In the presence of a strong base, these undergo what is essentially a Wittig reaction to generate something that can't be isolated, at least has not yet been isolated, namely a diazoethene. As far as I know, compounds of this have never been isolated, but they are obviously of extreme importance in this connection, because they lose nitrogen under the reaction conditions generating this type of species. And if the reaction is carried out in the presence of an olefin, one can obtain reasonably good yields of these alkylidine cyclopropanes, even when the starting ketone has a tertiary butyl group at that position. And with this methyl tertiary butyl ketone, for example, about 50% yield of this cycloadduct was realized. So that became available in 1979, and we immediately plunged into a study of the application of this kind of chemistry to 3 systems in which tertiary butyl substitution was gradually increased in the precursor ketone. Here is this phosphonate reagent, And the target molecules now are this monotertiary butyl, tertiary butyl dimethyl, and the ditertiary butyl bicyclo-3,1,0-hex-1-ene. When this reaction was applied to the monotertiary butyl case, shown here, the result was the formation of the sigma plus pi dimer in high yield. In other words, even the tertiary butyl group is insufficiently bulky to diminish the reactivity of this double bond to the point where one could isolate the monomeric compound. The presence of that group has changed the mode selectivity. That is to say, there is none of the pi plus pi dimer that we found when the methyl group was at this position. But nevertheless, dimerization is the only, or virtually the only, result observed. So that was a disappointment. But we reasoned that perhaps with two methyl groups at this site, that would add sufficient additional bulk so that one might be able to see monomeric product. And we treated this ketone with a tertiary butyl group here, gem dimethyl substitution at the terminal double bond with the diazophosphonate reagent and butyl lithium, and we obtained a preparation. This reaction is carried out at low temperature. This preparation, when treated with aqueous ammonium chloride at 25 degrees, gave two products. Now, you can see how badly we wanted this, because even when I drew this slide, I couldn't help but draw it. That's not the compound we obtained. It's the one with a double bond down here. So I apologize for that error. These are the two products formed in high yield from this cyclization. But the striking thing is that they are monomers, and that's the first time that monomeric products have been found in the Kerbrich cyclization. So we were very excited and wondered what is in this reaction mixture that is surviving long enough to be treated with ammonium chloride at room temperature. And so the next obvious thing to do was to try to isolate this compound by more conventional means, namely distillation. And one can distill a compound from that which has all of the correct properties, volatility, molecular weight, to be a monomer, but again, it is not the bicyclo-3,1,0-hex-1-ene. Surprisingly, what it is, or perhaps not surprisingly in retrospect, is this alkylidine bicyclo-2,1,0-pentane with a tertiary butyl group at this position. Now, this is the first persistent alkylidine bicyclo-2,1,0-pentane that we've obtained. It's stable at room temperature indefinitely. It's exquisitely sensitive to acid, and if it is heated to 75 degrees centigrade, it slowly and reluctantly goes away. What it goes to is this open chain diene, the same compound obtained over here. We don't know that this is a thermal reaction. It's conceivable that may be caused by adventitious acid catalysis in the glass, but in any case, this is a lower limit for the threshold temperature for the thermal decomposition of this compound. It's really fantastically stable for a substance of that structure. Now, just to give you an idea, something is, yes, okay. What we believe is happening is that the Kerbrich ring closure does take place to give this compound, which at temperatures, some temperature below 25 degrees centigrade, undergoes the alkylidine cyclopropane rearrangement to give the bicyclo-2,1,0 structure. And again, the equilibrium constant here is apparently very much larger than 1, which accounts for the fact that the product that we see has only that form. Now, to compare this compound, the tertiary butyl substituted derivative, with the other members of the series that we prepared, I show in the right-hand column some threshold temperatures. The unsubstituted one is unstable above about minus 60 centigrade. The dimethyl one we've talked about minus 40. The methoxy one is stable up to plus 5. And this one is stable up to at least 75 degrees. In terms of activation energy for the thermal cleavage of this bond, we can see that the presence of this tertiary butyl group has strengthened this carbon-carbon bond by about 11 kilocalories per mole. Now, the chemical origin of that 11 kilocalories is not difficult to discern, because the reaction that we are looking for is the formation of the trimethylene methane dimers. That requires the formation of the triplet biradical as a precursor. The triplet biradical, in order to be stable, must be planar. And if you cleave that bond when R is tertiary butyl, then you have a terrible allylic strain between the tertiary butyl group and the methyl group, and that is apparently worth at least 10 or 11 kilocalories per mole. And that's what protects that compound. Now, to return for a moment to the bicyclo-210 pentane chemistry, we have studied very recently some cycloaddition reactions of this molecule. And it seems to behave differently from either the Gassman-Cairncross kind of chemistry that we saw with just bicyclo-210 pentane itself, the saturated hydrocarbon, or from the chemistry that we had observed with the alkylidene bicyclopentane, where there was no tertiary butyl group here. This seems to be still a third kind of cycloaddition chemistry. We don't understand it fully, but I can tell you what the preliminary results are, at least in a qualitative sense. The reaction is definitely not a second-order reaction. And with the acetylene dicarboxylate, for example, at 25 degrees, this reaction goes quite smoothly. The products that one obtains, two of them shown at the lower right of the slide, are analogous to those that Gassman and Cairncross saw in their cycloaddition chemistry, namely ene products and cycloadducts. But the third product, which is formed in substantial amount, cannot be accounted for on that basis, we believe. And in fact, we believe the only reasonable intermediate to generate this structure is the one shown here. That is, it's zwitterion. I've arbitrarily shown that as the common precursor of these two other products, although that's not a necessary feature. Those could be formed by other mechanisms. But it's very difficult to see how a biradical intermediate, for example, could form this rearranged product, which no longer contains a tertiary butyl group. And you see what's happened here is the tertiary butyl group has been broken up, a methyl group has moved to that position, and now cyclization has occurred there to give this bicyclic compound. So exactly how one gets from these precursors to that zwitterion is not yet known, and we hope to find out eventually how that happens. But that is still a different chemistry. Well, now we've failed twice to make a bicyclo 310-hex-1-ene. Here's another chance at it with two tertiary butyl groups in these positions. And the idea here is that we thought that we had outsmarted this molecule now, because what it wants to do is to rearrange to a bicyclo-210 pentane. But we said, we got you now, because if you do that, you will put two tertiary butyl groups cheek by jowl and in an eclipsed conformation, an unavoidable clash of very large groups. And that kind of steric interference is worth, from data in the literature, probably about 10 kilocalories per mole, perhaps more. And so one asks the question, is it conceivable that with this substitution pattern, the equilibrium constant can be inverted, or at least modified, and the reaction driven back to this side of the equilibrium? Well, the answer, of course, is that these molecules are really much smarter than we are, And we had a moment's thrill when this reaction was carried out. This ketone, 2 tertiary butyl groups here, terminal methylene, this Gilbert style reagent was used, and there was isolated from the reaction mixture in good yield a single monomeric product. But it was quickly evident that it was not the bicyclo-310-hex-1-ene, but instead was this di-tertiary butyl methyl cyclopentadiene, obtained by a hydrogen shift from the ring position into that point. That is a reaction that takes place at some temperature below 25 degrees centigrade. We believe it's intramolecular and thermal. The exact mechanism perhaps is speculative. But neither of these 2 compounds is formed, and an escape hatch that we had not anticipated was cleverly found by this molecule. So we have been close but no cigar. Now, one final approach that we are investigating, I just want to tell you about briefly. This work began with the study of the high temperature chemistry of these biradicals generated in flash vacuum pyrolysis with a residence time of about 20 milliseconds, 600 degrees centigrade. This diazine loses nitrogen very rapidly and gives the products shown here. Now, this triene, cross-conjugated triene, of course, results just from cleavage of the carbon-carbon bond at the back of this bridge. This is a hydrogen shift product, which is easy to imagine obtaining from the biradical that would be generated by deazotation. This is a secondary product from hydrogen shift here. And there's a very interesting product, X, whose nature we did not know for a long time, but which we discovered serendipitously in the study of another reaction of the biradical carried out under conditions about as diametrically opposed to the ones shown here as one could imagine. This is the photolysis at minus 196 degrees centigrade of the species generated when that diazine is photolysed, namely this triplet biradical. And when that preparation is photolysed at 310 nanometers, the same products I showed you on the previous slide, namely the open chain triene and its transformation products and that cyclic diene, are formed. But in addition to that, this olefinic alkyne, terminal alkyne, is formed. This product is almost the exclusive product when the reaction is carried out in ether glass, and it's formed at about 40% of the product mixture in hydrocarbon glasses. At first glance, this is really an astonishing transformation, but when you think about it for a moment, you see that this could be derived if this biradical were to close between these 2 positions to give this bicyclo-310-hex-1-ene, which then can undergo a retrocarbene reaction by cleavage of these 2 bonds to give this intermediate, which is a vinylidene. Now, of course, we've seen this type of vinylidene cyclize in this position, but that simply means this reaction may be reversible. But what has never been the case before in the work that we have done is the presence of a hydrogen at the end of this double bond. Hydrogen being an easily movable group in contrast to alkyl, this alkylidene has an escape route that is not available to the alkylidenes that we had generated previously. And it does that by migration to give this terminal alkyne. Now, I should mention that the exact mechanism of these transformations, which of these are excited state reactions and which are ground state reactions, is still under investigation. I should point out that there seems to be little question that this material must be formed in some sort of excited state, because the well, I shouldn't say there seems to be no question. It is probable that this is formed in an excited state. The reason that I say that is that there is precedent in the literature, in the work of Brinton and also of Kendi and of Gilbert, that shows that methylene cyclopropanes undergo this retrocarbene cleavage photochemically. There is no thermal precedent for this reaction. So it may be that this transformation can occur thermally if the strain energy is high enough. That remains to be established. Now, one might think that it should be possible to get back into this energy surface starting with this terminal alkyne, because in principle all one has to do is to just reverse these steps to shift the hydrogen back to here, cyclize to the bicyclo 310-hex-1-ene, and then open that bond, and that will take one back into this manifold and the products derived from it. And on the next slide, I show the result of this experiment, which has recently been carried out. This is pyrolysis at 700 degrees, a residence time of about 20 milliseconds. This terminal alkyne does, in fact, give these same products that we saw when the biradical was generated from the diazine, namely this cross-conjugated triene and this monocyclic diene. And we believe that is taking place by the thermal reversal of that photochemical reaction that we saw earlier, which must then pass through a bicyclo 310-hexene intermediate. And what this observation tells us now is that we can do the Kurbrych-style ring closure in the gas phase. And that leads to the possibility, we hope, that it may be possible to trap this on a cold window before it has a chance to become reactivated and go on to these products. That may be a vain hope. There are other possibilities that we are investigating, but at least it is going to be examined. On this slide, I show the names of the persons who have done this work. Richard Salinaro did all the work on the tertiary butyl substituted systems that I have talked about. Mark Mazer did the kinetics of the thermal reactions of alkylidine bicyclo 210 pentanes, and he and Alan Pinhas and Matthew Platts were responsible for the photochemical study. Mark Rule and Mike Lazaro were the ones who solved the synthetic problem of making alkylidine bicyclopentanes. There is one name left off here, and I apologize to Stephen Potter, who was the one who carried out the original work on the high-temperature chemistry of the diazine. These granting agencies have kindly lent us their support. I thank all of these people and agencies, and I thank you for your kind attention.